Hello everyone, thank you for joining me. Our electrical infrastructure relies on high voltage substations, and at the heart of every substation lies the bus bar. If you think of a power system as a circulator network, the bus bar is the outer, the critical connection point. Today we're diving into the essential topic, bus bar protection. For the first slide, the bus bar and the need for protection. Let's start simply. What is the bus bar? It's an electrical junction where multiple incoming power sources, outgoing feeders, and critical equipment like generator, transformers meet. It provides a system with flexibility, allowing us to switch power path as needed. But that flexible comes with a massive liability. Why is bus bar protection critical? Because a bus bar is a single point of failure. A fault of transmission line only takes that line out. A fault on a bus bar takes every single connected circuit out. This is a massive power outage and it leads to system instability. Therefore, bus bar faults demands two things. First is the maximum speed. Fault clearance must be incredibly fast, typically less than 3 cycles or about 50 milliseconds, to minimize physical damage and prevent the entire system from falling out of synchronism. Second is the absolute selectivity. We only want to treat the necessary breakers when the fault is inside the bus zone, and we must remain completely stable when the fault is outside the zone. Next slide is about the challenge in bus bar protection. Bus bar protection is one of the most challenging areas in protection engineering, mainly due to four issues. The first and most significant is CT saturation. A typical bus bar has many connected circuits, each with its own current transformers. During the external fault, a massive short circuit just outside the bus zone, the huge fault current can cause one or more CTs to saturate faster than the others. When one CT saturates, it starts accurately mirroring the primary current. Second is we have the CT matching and ratio errors. Getting 15 or different 20 CTs to behave identically is nearly impossible. Small manufacturing differences called spill current must be managed. The third is system flexibility. Bus bars are constantly being switched and reconfigured. Sections are isolated, transfer bus bar are used. The protection schemes must adapt automatically to this changing topology, logically isolating the cities of circuits that are disconnected. Finally, we must always consider breaker failure. So if the bus bar protection sends a trip signal and one circuit breaker fails to open, we need a rapid backup plan, which we address with breaker failure protection or BFP. Next slide is about the bus bar protection schemes overview. To address these challenges, we categorize protection into two groups. The primary choice is zone-based differential protection. This scheme compares the total current entering the bus with the total current leaving the bus. If the sum is anything other than zero, it means current is going into a fault inside zone. And with trip, it is fast and highly selective. Our backup is usually non-differential, using time delay over current or distance relays on the feeders. It's simply but it's slow and non-selective, meaning it trips more lines than necessary. Moving forward, we will focus solely on the primary solutions, differential schemes, which come into two flavors, high impedance and low impedance. High impedance differential protection. The high impedance scheme is the classic traditional method. Prized for its inherent stability, the main idea is to include the stability resistor in the differential path, which creates a high impedance voltage across the relay. During a normal external fault where CT saturation is the risk, this high impedance does two crucial things. One, it limits the small false current caused by the saturated CTs to a level far below the relay's pickup setting. This ensures the relay does not trip. Instability is maintained. 2. We also use a nonlinear voltage limiting device like a metro seal to safely shunt the very high voltage generated by the saturated cities, protecting the relay and wiring. Conversely, during a true internal fault, all healthy cities contribute current, and the high voltage developed across ours easily forces at past trip. The advantage of this scheme is its powerful inherent stability against external faults. And lastly is the low impedance differential protection. The low impedance scheme is the modern microprocessor based approach, now the industry standard for new installation. Instead of relying on a physical stabilizing resistor, it uses software algorithms to manage stability. The principle of operation is based on bias differential protection. The numerical relay calculates two values, the differential current and the restraint current. A trip only occurs if diff is greater than threshold that is proportional to I bias. The real power here relies in the advanced features. CT saturation detections, the relay analyzes the current waveform for distortion using algorithms like harmonic restraints to detect saturation. If saturation is detected during an external fault, the relay temporarily blocks the trips. Dynamic bus replication, this is the key. The relay uses auxiliary contacts from isolators and breakers to automatically, logically redefine the protection zone whenever the bus structure is switched. This flexibility allows for cities with different ratios to be used as the relay handles ratio making internally. So that's all.